Okay, so my name is Thomas Padioleau. I work at Maison de la Simulation as a CA research engineer. I work on Kokkos. I'm a Kokkos developer. And this work is also presented by the SYCL team, which is a team at CA that works on Kokkos. So Kokkos on GPU and actually also on CPU. So why Kokkos does exist? Well, in the HPC community, we're facing some few challenges. Among them, we are facing hardware diversity. With the arrival of the exascale, this led to the introduction of GPUs on supercomputers. As you can see on the right, on the table, you can see the first the most powerful supercomputers from the top 500 ranking. For the rank 1, we have El Capitan, which is equipped with AMD GPUs, actually APUs, the AMD MI300A. The second one, Frontier, a bit older, is equipped with discrete GPUs, MI250. At the third position, Aurora with Intel GPUs, and NVIDIA GPUs for Jupyter, which is a German supercomputer, and the last one from Microsoft Azure with proper NVIDIA GPUs. So we have these different vendors that equip the supercomputers, and all provide different technologies to target them, either CUDA, HEAP, or SYCL for Intel. And this can lead to code duplication in some cases to support all of them. So the need is to have some API that can target all of them at once. And this is why this is where Kokkos comes into play, to offer some performance portability, a single API that will allow us to target all of them and simplify the work for developers to target all the GPUs and even CPUs. So what is Kokkos? As I said, it's a modern C++ library for that targets shared memory parallelism. So it does not support by itself distributed memory parallelism as you would do with API, for example. And it targets data parallelism. So when you want to execute the same instructions on different data. It heavily uses template metaprogramming and function objects or lambdas that you have already encountered. And it aims also to follow the C++ standard. And actually, it also contributes to the standard. And as a note, the next version, the version 5, will support as a minimal requirement the C++20. So the goal is to support the GPUs, of course, so AMD, NVIDIA, and Intel GPUs, but also to support multi-core CPUs. And all of that using some existing, what we call backends, that work well on the different architectures that we support. As for the contributors and developers of the Kokkos library, it originally started with Sandia, where actually Kokkos was part of a bigger project called Trilinos. It was then extracted to, as it could be seen that it could be useful for the projects. Then the Oak Ridge National Laboratory joined the effort, and more recently, the CEA in France joined also the main developers of Kokkos. There are many more developers that are not listed here. And it keeps growing, also related to that now it's part of the Linux HPSF Foundation, so the High Performance Software Foundation. that has now 1 year. So let's dive into a simple example. So on the left, you have a sequential pure C++ code, so the main function, where we want to initialize a two-dimensional array. So let's say a C++20 example. We have an array of 2 dimensions, one that is where the size is known at compile time, so that would be the nvar variable, and one size that is only known at runtime. And then we allocate some data, some integer data here with the new keyword. And then we initialize it with a sequential for loop that will loop over the runtime dimension, and where we initialize to some value the array. Note that in this case, we do the linearization. It's a two-dimensional array, so we allocate one big one-dimensional array in memory, and we interpret it as a two-dimensional array by linearizing ix and here these anonymous variables. This example on the left only works for CPU as such. And on the right side, we have a Kokkos version of this example, where we start with some initialization of the library that will also provide the finalization. We keep our 2 dimensions, and then we create one of the data structures provided by Kokkos, a Kokkos view. Note that we have to pass some template parameters that I will detail later. But this is the equivalent of the sequential example. So we say here that we want a 2-dimensional array. We call the constructor of the class by passing some label and only the runtime dimension, because the compile time dimension is already known through the template parameters. And then instead of doing a sequential for loop, we call a function called parallel for. So this is quite similar to SYCL. You pass a label again, the number of iterations that you want to make, nx, so that mimics the sequential loop. And then you pass here, in this case, a lambda. So the lambda takes an integer as an input parameter, and that we use and that we pass in the function call operator of array. So instead of doing, as in the sequential example, a linearization by hand, we just use the function call operator that will do the linearization for us. So as you would do also in Fortran or NumPy. And with this version of it, we can run on CPU or GPU, depending on how we compile the code. So let's dive in more in detail into the Kokkos programming model. So the idea, as I said, is to write once and run anywhere. This is done by recompiling the code. So each time you want to, so you write your code once, and you recompile it to target a new architecture. So you get different binaries depending on the architecture that you target. Kokkos mimics and introduces a concept that mimics the hardware. So it is based on an abstract model for the hardware that you can have that you can see on the right. So an abstract node would be equipped with some memory that will be here in green, and that will be mimicked in the Kokkos model by memory spaces. and by also execution spaces that will mimic the execution resources that we can have on the node, either the cores or the accelerators in yellow. And as we have seen, it also provides some multidimensional arrays that are very important in scientific computing. To do the parallel work, Kokkos introduces some basic patterns. We have 3 patterns: parallel for, parallel reduce, and parallel scan. So the parallel for is just a parallelized loop where each iteration must be independent, and the user has the responsibility to avoid any data race in the function that is passed to the parallel for. So this is the same as the first example. The parallel reduce will allow you to, for example, do a sum over an array or any kind of operation. This changes a bit the signature of the function that you pass to Kokkos. So you still get an integer that will identify the loop iteration, but you also have a local reducer that is private to the thread calling the function that will have a local version of the reducer, and that will, at the end, contribute to a global variable that is passed as the final argument of the parallel reduce. And then you have also a less common pattern that is the parallel scan that is also sometimes called prefix algorithm or cumulative sum in NumPy that will basically do, if you call a parallel scan over n, you will basically do n reductions. All these functions dispatch asynchronously, but they are sequential with respect to each other. So when, for example, the host calls the parallel for, it will launch a kernel, but it returns immediately. It doesn't wait for the result of the parallel for. And if again you launch a new parallel algorithm for example, the parallel reduce, it doesn't wait, but you are ensured that the 2 parallel algorithms are sequential with respect to each other. And if you need the host to wait for some results, you can call a barrier that is called in Kokkos fence to wait for the result. You can have a finer control over the way you launch the parallel algorithms that are called execution policies. We have 2 big families. The first one is the basic parallelism, which is then divided into 2 policies. The range policy that we already encountered, in fact, when we passed only n as an argument of the parallel for, it was a shortcut for this policy. And we have the MD range policy that will allow you to get multidimensional loops. So instead of getting only 1 integer, you can go to 8 dimensions, and you will get here as an input parameter of the lambda 8 integers. So that can be useful, for example, for stencils. And it's also a tiled iteration space, and you can control the iteration order of each dimension. The second execution policy that I mentioned is the hierarchical parallelism. One thing that you cannot do with the previous one is to nest parallel fors. Once you have already launched a parallel for here, you cannot call a new parallel for inside, even though you could have some degree of parallelism available inside this parallel for. That is what allows you the hierarchical parallelism. So again, we call a parallel for, but instead of passing range policy or simple integer, you pass a team policy that will not get you an integer. It will get you a handle that is called team handle here. And then inside, you can call again a new parallel for, but this time bypassing the team. So this matches the hierarchical structure of the hardware and the GPU, for example. You can also have access to a finer memory, like the scratch memory on GPUs, or what is called shared memory on CUDA. And at the inner levels, you have new execution policies, team thread, thread vector, and team vector that you can pass at the inner part. Again, you have either a one-dimensional or multi-dimensional range policy at the inner levels. And finally, regarding the execution part of Kokkos, Kokkos introduces the execution spaces that I mentioned earlier. For example, they will select the backend that you want to use. So for example, we have CUDA, heap, or SYCL for the device part, and for the host part, we have OpenMP or Serial. They are not all available at any time. So to be portable, we advise you to use some aliases that are predefined by Kokkos, and that will, depending on the compile options that you choose for Kokkos, be aliases to CUDA, heap, or SYCL. And if we take again the example of the range policy, instead of passing a begin, an end, and a chunk size, you can add a first parameter to pass the execution space instance. So here you could, for example, pass either default execution space to target, if you compile for GPU, to target a GPU, and default host execution space that will target CPU backend, even though you compile for GPU, if you want to ensure to run on the host. Now, regarding the memory aspect of Kokkos, Kokkos introduces the Kokkos view, which is the main container of Kokkos that is templated by different important parameters. So it's a multidimensional array, as you would have in Fortran or in NumPy. So the parameters are the data type, the type of data that you want to store in memory. And Kokkos allows you to control also the layout that I will detail later, the memory space, where you want the data to reside, and some other aspects of the way you want to access the data. Regarding the copy semantics, it behaves like NumPy arrays, it's shared semantics. So if you call A equal B between two views, you will not overwrite, you will not have a deep copy. It behaves like a stud pointer, if you know. If you want really, if you really have two different allocations and you want a deep copy between the two, you have a dedicated function for that is called deep copy. We have also some features to allow you to control mirrors between host and device if you want to pass data from the host and the device. And it's also, since recently, compatible with the NDSpan. That was actually kind of the first implementation of NDSpan. This is the Kokkos team that proposed the NDSpan to the standard library of C++. So I mentioned some template parameters. So one of them is the memory space. So this is how you choose where you want the data to reside. So when you are on the nodes of supercomputers, you have different memory spaces that are not all available from anywhere. So we want to control where the data resides. So Kokkos introduces some of them, the host space, CUDA space, or the UVM. And again, like for the execution spaces, to get some portability, we want to either use aliases or the memory space that are attached to the execution spaces. So we have the host space that is portable, but to get the default or preferred memory space of a given execution space, you can get it from the alias injected in the class. We have also shared space. That is the memory that you can access from anywhere, from the host and the device. And the scratch space that you want to allocate using hierarchical parallelism. Another aspect of the Kokkos views is the memory layout, which is an important aspect when you manipulate multidimensional arrays. That is how you interpret your one big array that is stored in memory. So Kokkos introduces 3 of them: the layout right, left, and stride. So they all follow this kind of formula. So if the I variables are the indices that you pass to the Kokkos view, so here in the case of 4-dimensional array, you pass I0 to I3. They all follow this kind of formula, but depending on the strong typing, this enforces different values for what we call the strides, here noted S. For the case of the layout right, this forces the last stride to be equal to 1. The case of the layout left, the first stride is 1. And for the layout stride, it can be anything. You typically get it when you take subviews of views. Kokkos is also more than that. It introduces other containers that I will not mention much. Offset views that are arrays that do not start at 0, like in Fortran. Dual views that will help you to manipulate data that is on the host and on the device. It contains 2 views. One that is always on the host and one that is on the device, and helpers like if you want to synchronize the data between the host and device, it results to be no hope when you compile only for CPU, and there is an actual copy if you compile for GPU, for example. Scatter views that are algorithms related to the atomics. The SIND classes if you want to do some explicit vectorization. Regarding algorithms, recently we introduced some standard-like algorithms. So algorithms that are accelerated by the Kokkos implementations. Some sorting algorithm, random number generation, and also some helpers, less critical, but that can be quite useful. A printf that you can call from the GPU, the Kokkos numbers that are the stud numbers actually, and some also structures like pair or tuple that are actually really close to the standard implementation, but with the annotations that you need to generate functions for the GPU. That is for the Kokkos core, and Kokkos has also some ecosystem. So in this diagram, Kokkos is at the bottom, what I talked earlier. And on top of that, we have also other libraries. So for example, KokkosKernels that will bring you some linear algebra features that you may need when you build a real application. That can also bring some ODE solvers, ordinary differential equation solvers. We worked on a portable KokkosFFT, so that reuses the vendor libraries, but with a Kokkos View API. Other projects like KokkosCom that will reduces the gap between distributed memory parallelism and Kokkos. Some Python binding. On top of that, we can build then real-world applications. We have some also tools that will help you to debug and profile the Kokkos applications, and we also do some support by improving the documentation, doing some trainings or communications like today. If you want further reading, I can advise you some of the articles that were published regarding Kokkos. We have, of course, the GitHub repository. We have a wiki for the official documentation. A few years ago, there was also a tutorial made by Christian Trott, the main developer of Kokkos, that is on YouTube. So as a conclusion, I hope I showed you that Kokkos can provide you some performance portability by abstracting the hardware. It's easy to adopt in C++ code base, and it's a quite active and widely supported project. And I will thank you for your attention. You have any question?
Maybe
Yes.
one very simple question. What are the main differences between Kokkos and SYCL for you?
For the core parts?
Yeah.
One main difference could be the dimensionality. We go higher than 3 dimensions. SYCL, I think, chose to be as close as possible to the hardware or to the backends like CUDA that supports only 3 dimensions. Kokkos will try to go higher. We have some applications that need higher dimensions. On the other hand, SYCL may have some more flexibility as it can allow you to choose at runtime where to run, whereas with Kokkos, you would do this choice at compile time. I think these are 2 differences that I can think of.
When did you start developing Kokkos?
Myself?
Well, where was Kokkos?
Kokkos started like 10 years ago now. Myself, I started like in 2017. I started my PhD. If you can read. We are almost releasing the version 1. In the coming months, it should be released. We support all the major backends of Kokkos. We support KokkosFFT. So we use the backends, the vendor libraries. So KokkosFFT for CUDA, HeapFFT for heap, and the 1MKL for SYCL, and FFTW for the OpenMP and serial backends. All of them are supported. We don't have the support for less common backends in Kokkos like OpenMP offload and OpenACC. But feel free to, it's on GitHub and people are free to open issues if they have any.
And we do have another question on Discord from Adrien. I'm not sure to understand. Using Kokkos means that separate part of the same code can be compiled with different kind of parallelism, serial, CPU, and GPU, or do we need to choose between CPU and GPU at some point?
So you basically choose between default execution space and default host execution space in your source code. And then at compile time, you can choose whether you want to enable CUDA, heap, or SYCL, or OpenMP. You cannot enable all of them at once. It doesn't make sense for Kokkos. So you typically choose at compile time one of the device available and one or two for the host. You can enable serial and OpenMP or threads, and one of the devices like CUDA, heap, or SYCL.
Thank you.
Just one point, because people may be confused seeing Kokkos using SYCL as backend, and now SYCL having backend towards other materials. So each portability layer sometimes use others as backends. So you have a pile of backends, but there in general, SYCL is used as a backend to the Intel GPU.
Yes, exactly.
That's why Kokkos use SYCL, just for the Intel GPUs.
Yeah, that's what Intel told the Kokkos team to use to target the Intel GPUs.
Yeah.
That's
That's why we have a portability layer using another portability layer.
Exactly. Actually, it's more I think one API that we support. Not sure we have ever tested adaptive C++ for the Kokkos backend of Intel.
Another Discord question. How does Kokkos performance compare against CUDA on NVIDIA GPU?
It can add small overhead because there is some abstraction that is added on top of CUDA, but basically for 1D range policy, you get the performance that you would have with CUDA. The overhead is really minimal. You can notice some overhead with MD range policy that is known to have some performance issues, but this is also a work in progress. But other than that, the performance overhead is minimal.
Thank you.